So it's with really, truly great pleasure that I introduce the next speaker, Dr. David Brady, to talk about nutrigenomics and precision lifestyle medicine. Dr. Brady was really one of, if not the exemplar of precision lifestyle medicine. He is so precise in what he does, and not only teaching, but actually developing scientific tools for us to be able to better understand the body. Being a CME, of course, I can't say what those are, but you'll be able to figure it out. And so it's interesting. He's on the advisory board for this conference, and he's been an incredible contributor to the broad range of people that we have coming here. He is also a frequent lecturer here, and when I first saw his slides many years ago, maybe a decade ago, it blew me away because I have to look at every slide of every lecture for CME to make sure that they're evidence-based for certification. And when I saw his, it was the cleanest, most amazing evidence-based presentation I've seen. Maybe I'm excluding Jeff Bland, but I actually asked the board if we could ask his permission to use his slides to give to some of the people who needed the remedial education on doing evidence-based presentations. You'll see he's going to be talking about a complex topic and making it very simple for us today with a new tool that's incredibly useful for the clinician. Very hard to figure out on your own. I've tried, and I'm looking forward to learning more about it today. So in terms of academic qualifications, he's a licensed naturopathic physician in both Connecticut and Vermont, and board certified in functional medicine and clinical nutrition. He serves as he's an associate professor of clinical sciences at the University of Bridgeport, and has a private practice in Fairfield, Connecticut, which I've referred patients not infrequently to him for consultations, especially for some of the functional medicine testing and evaluation that we're actually not allowed to do in New York, and has published multiple papers on and textbook chapters including chronic pain, autoimmunity, functional gastroenterology. But that's, I think, the end of the introduction. Dr. Brady is going to speak for himself. So you'll see this is a real treat. So it's a great pleasure to introduce my friend and colleague, David Brady.
Hello, everybody. How are you? Thank you, Dr. Merrill. I appreciate that. Well, as Dr. Merrill said, I've spoken many, many times at IHS. It's really one of my favorite events of the year. It's a wonderful conference, and the people who run it are great too. So it's a pleasure to be on their advisory board. And I think this is probably the 6th or 7th year I've been speaking in a row, but usually I have a very well thought out, organized, evidence-based type of presentation like Dr. Merrill was suggesting. And today I have nothing of the sort. Today I'm just going to show you some toys I've been playing with, and hopefully you think you will think they're as cool as I do, and it might give you a little glimpse into the future, kind of where we're all going to be going as clinicians, where some of us are dabbling in already, but I think the landscape for us in functional and integrative medicine, even healthcare in general, is going to dramatically change very, very rapidly, and we'll look at and how that may happen and how it will impact you. And we're going to look at this topic of nutrigenomics and precision and personalized or lifestyle medicine. And we're going to look at how we're trying to take the lessons that we've been able to learn, I mean collectively, not me personally, but just collectively from big data and analytics and AI and machine learning and network theory and so forth. And how do we make that actionable at the bedside? How do we really bring it into our practices? Because that's where a lot of us struggle, right? We all know that this stuff is coming. We all see the value in it, but we really struggle. How do we deal with this on a personal basis as a practitioner, but also with our individual patients in front of us? So just my disclosures, I am the Chief Medical Officer of Designs for Health in the nutraceutical space and of Diagnostic Solutions Lab in the diagnostic services space. So let's talk about this thing we call biochemical individuality, right? We know that human physiology is influenced by various biochemical processes, which in part are influenced by one's genotype. There's a lot of different influences out there, environmental influences, the exposome. We'll chat about several different types of omics, if you will, in this presentation, although it will center mainly around genomics. But biochemical individuality is a major pillar in the practice of precision functional medicine. However, it is my opinion, and I think it's shared by a lot of people, maybe it's shared by you, that there's a lot of talk about personalized medicine or personalization. There's a lot of talk about precision in functional and integrative medicine, and I don't see a lot of it happening, honestly. I still see a lot of people basing practices on 30-year-old subjective questionnaires that were never really rigorously tested for their utility, in different types of constructs that have been created, or matrices, or whatever you want to call them, that attempt to get personalized or individualized, trying to extract out different, antecedents and triggers and mediators and all those types of things, but they're really, in the end, kind of quite primitive. And then on the other end, we have all these big data analytics coming out of research, which is also an entirely different thing. So we need to figure out how to truly make integrative and functional medicine models more precise and more personalized. And one of the tools we have to do that, one of the leverage points, is to look at a person's genomics, or their SNPs, if you will, their single nucleotide polymorphisms, because they largely influence our biochemical individuality. However, I see the use of SNPs over the last, since they've emerged and become more common, in the last decade or so, I see SNPs being misused all the time. I see people that base their entire practice, they're the genomic queen, or whatever they call them, or the genomic king, or whatever. You come in and get your nutritional thing, and they're giving you very, very precise protocols based on single analysis of one SNP, right? They're making too much of one SNP. There are SNPs that are, really, really impactful and very associated with specific pathologies and stuff, but it's really where the gold to be harvested is not in a single SNP. It's in pattern analysis of a multitude of different SNPs and a multitude of different metabolic tendencies of an individual. That's where we can really make an impact. So I want to see us move beyond that. And much of what's being used was created not for the medical diagnostic decision-making clinician or this whole space. It was created for direct-to-consumer products, really slick apps with a bunch of SNPs that give you very generalized information in the end. Some basic dietary information, how you should maybe exercise in some very gross way, right? Or maybe one supplement or two that you should take, but it's not really precision, and it's not really all that personalized when it all comes down to it. So it kind of leaves people somewhat disenchanted after they do many of these tests, get the reports back, and then they don't do it. You can't even do what the simple stuff they're told to do. And one of the challenges is when we start looking into genomics, or microbiomics, or metabolomics, or proteomics, or glycomics, any of the omics, right? It can get very complicated very quickly, especially when we're dealing with these big, large data sets, and how do we make heads or tails of it? So complex systems are messy, and humans make errors when they try to deal with them, and we don't have a lot of time. Has anyone had the pleasant experience of having someone walk in your office and plop down their inch-thick data file from a 23andMe? Or a uBiome, right? Hey, look at this, doc, what do I do with this? I'm like, I have no idea. I don't even know what most of those things are, right? So I'm sure you've been in the same situation. It's just not in a usable format, right? Or then you can run it through one of these genetic genies, and then you're back to almost like a direct-to-consumer, kind of almost, it's reduced to silliness. So is there a middle ground? There is, and these tools will get better and better. Is it necessary? Well, when they survey medical providers and healthcare practitioners, 67% of them believe that artificial intelligence has the potential to transform healthcare delivery. But only 10% of them think that their organization is prepared to meet this technological infrastructure, right? That even has the ability to even contemplate such a thing. And only 4% think that their organization is prepared to use AI with the current staffing and in-house expertise that they have. So clearly there's sort of an understood need, but there's a gap in being able to deliver on it. And most of this survey was done with clinicians in large institutions, hospital systems, managed care systems. When you bring it down to the individual practice level, or even the small group practice level, the numbers are even more challenging. So we're going to look at a system that was put together that does enable a clinician to really mine through much of this stuff. And I'm going to give you a little flavor for it. I'm not going to teach you how to use the system per se, and I'm not going to give you a genomics lesson, but I want you to just get a feel, go on the ride with me on the kind of tools we're using and developing, and how this may be impacting you going forward. And I'm going to highlight some of the work that was done at my institution, the University of Bridgeport, where I was the vice president of health sciences for about 15 years and oversaw all of the health sciences programming in our healthcare system and the Nutrition Institute. But I brought in somebody who I really respect amazingly, and he's really is, you know, and I don't use this term lightly, he's a genius. And his name is Dr. Peter D'Adamo. And you may know him from the Eat Right for Your Type books and things like that. He's a multiple New York Times best-selling author, and his books are in every language around the planet. But a lot of people, that's all they know him for, and it's a very, very small part of what he's done. And we'll even touch back on that subject again as I go through here. But that's Peter right there. Peter's a naturopathic medical physician. He's an incredibly gifted clinician and doctor, but he's equally as gifted as a computer programmer and medical informatics expert. And he has all these different skills to put together along with team members that were built to be able to bring to you some of the things that we're going to talk about today. And this is some of his residents and postdoctoral students at the Center for Generative Medicine at the University of Bridgeport that was there for about 15 years that we formed together there. And you may have read about this center and some of the work that was done in the Townsend Letter feature and so forth. But let's just look at some of this stuff, and we're going to look at a particular medical informatics platform or a software platform known as Opus-23. And Opus-23 kind of lives in a couple of different iterations. The original one is Opus-23 Pro. It's meant to be the highest level professional sort of iteration of this medical information database and analytics tool. And it's meant for people who've gone through very intensive training with Peter and with the Center of Excellence. Very, very high level users, many researchers, many different types of clinicians. And it's incredibly powerful, has a lot of different apps and different functionalities hanging on it that would not necessarily be something that would be used all the time by the practicing clinician. And sort of the barrier of entry into it is high, but it has an amazing utility to it. So I worked with Peter, and we worked with him as a team with DSL to try to change the user interface and make it much more utilizable, digestible, and lower barrier of entry for the clinician. But what Opus essentially does is it real-time talks to and integrates with many of the publicly held and available metadata bases out there, such as genome-wide association database, ClinVar, things that attach different associations between genomics patterns and different disease patterns, but also everything from taxon and mesh and dbSNP. And so we know we're all talking the same language when we're talking about different SNPs and different RS numbers that, you know, when you're all referencing the same thing. KEG for metabolic pathways, and Etiome for different etiological type of associations, pharmacogenomic databases, agent IDs. So we know different drugs, different natural agents, herbals, nutraceuticals, they all have agent IDs that can be tagged, and we can then mine associations in the data sets or in PubMed. So the system also crawls real time through PubMed. Right? So it's crawling through the medical databases as they're emerging and literature's coming out, it's staying current, and it's cross-referencing with all the metadata and the different associations that are made in the literature. And some of this is done through automation, and some of this is done through actually human curation with experts that are surveilling these things and updating the system. And Peter has some very skilled people, and the lab has some very skilled people that do this. But before we start, let's just get a couple of terms straight. Genetics versus genomics. Genetics is the study of genes and inheritance. So often genetics assesses single genes within the context of congenital disorders such as cystic fibrosis, PKU, muscular dystrophy, et cetera. So these are really hardwired, like medical genetics type of stuff. That's basically not what we're doing when we're dealing in genomics in our practices. Genomics is more the studies of genes, their functions, and interactions with one another and the environment. So things that you're familiar with are like methyl tetrahydrofolate reductase, SNPs, different epigenetic and epistatic relationships, and pharmacogenomics. And epistasis and epigenetics, they're a little bit different as well. When we use the term, or when I use it today, epistatic relationship, epistasis is the interaction between different genes and their biological products, so protein interactions. Genetic is the interaction between genes, and epigenetic is between genes and the environment. And epigenetic and epistatic relationships are the reason why everyone doesn't have the same outcomes when they have similar genes, right? That there's a lot of different factors that are at play in all of this. And before we start drilling into it, one more thing to remember, and my friend Mark Hyman uses this term a lot, or this little phrase, that genetics loads the gun, but lifestyle fires it. Right? So we know that our genes aren't our destiny. It's the kind of hand of cards we have at a baseline to play, but we need to play them the right way. If we play them the wrong way, then the gun fires and it's a bad outcome. But if we play them the right way, we can stop that outcome from happening by and large with the kind of SNPs and the kind of pathways we're looking at. So, Opus-23 in particular, and including Opus-23 Explorer, which is this iteration I'm going to talk to you about today, unlike most of the other things that you're used to out there, your 23andMe and Ancestry and Genome and other things that are out there, they're meant for the consumer to just swab their mouth, send it in, and get some report back. It's not meant to have a healthcare provider or a knowledgeable intermediate in between to parse the data, to contextualize it, and to report it to the patient in a rational way. Therefore, even from a regulatory standpoint, these direct-to-consumer genetic platforms are restricted from reporting out significant SNPs of pathology and things where it's required to have a healthcare practitioner in the middle, or at least a genetic counselor, right? You don't want somebody getting directly in the mail some kind of horrific information about their genetics that they're going to go out and jump off a bridge, right? I mean, the regulators are very concerned about this. So it limits what those kind of platforms can do. The other limitation fact is they're trying to do these things really, really inexpensively, especially after they monetize the business model. For instance, 23andMe used to do the test for $99, remember, forever, and it had all these SNPs on it. And what they were doing is basically probably doing at the time about $200 to $300 worth of genetic sequencing for $99 to a lot of people. Why would they do that? You think this was a California, Silicon Valley startup. They're not stupid people. They're not in the business of losing money. They were enticing people to give over the genetic information to build a massive genetic database that they then sold to pharma, and that's where they made the money. So that was the monetization of it. It wasn't the $99 a pop. That was chump change, right? But once they sold off the metadata, now the business model had to substantiate itself, and they immediately removed about 38% of the SNPs on the test. Many of the ones that we were needing to use in these type of analytical systems for our purposes. And Ancestry was really developed from the beginning to really concentrate on ancestral genes, not medical and lifestyle and those type of things. So there really became a problem with where do we get the good data to put into the system, because the system is only as good as the data. And the construct here inherently is designed intentionally to include the clinician. The clinician is not cut out of this in a direct-to-consumer model. It's by intention kept in it because we feel that with this genetic information or genomic information or any kind of omics information, it's really much more valuable if it's contextualized by a clinician who's sitting there with the patient, who knows their medical history, their family medical history, understands their stressors, their lifestyle, what their diet is like, and so forth. So that's very, very important within all of this. So a clinician is there as the intermediate intermediate person. And one of the rules of Opus-23 Explorer is that there's no rules. So it's not a static report. And I'm here to tell you, if you don't realize it already, because it's going to come at you like a freight train, the days of your laboratory results, whatever the lab you're ordering is, particularly when you're dealing in microbiome or genomics or metabolomics or what have you, the days of getting a report in a static PDF are coming to a close. We're leading the edge here on what's going to happen. Your data is going to be delivered to you in an active medical informatics portal that you can mine and you can ask questions and you can query and you can do different things with. It's not a static report. There's too much data to report. Would you want to get a genomics report with a PDF with, even if you put nice little color graphics and visual analog scales and all these cartoons they put on them, right? Do you want to get one that's 67 pages long? With much of it not meaning anything in relation to your patient and their clinical state, right? So it's how we're going to get our information fed back to us is going to change. So we're going to look at some different sort of utilities or apps, as we call them, within the Explorer system that makes some of this easy. Now, we solved the data issue by actually developing at DSL our own chip. So our own sequencing technology, well, it's not our own sequencing technology. We're using the latest very high-end genomic sequencers, but it's a customized chip. And the chip actually assesses over 900,000 SNPs, including all the ones that were deleted from the direct-to-consumer platforms and including ones that are considered medical or diagnostic. So over 900,000 SNPs the data set contains, but in reality, right now, today, only about 6,000 of them are really useful to us because those are the ones that we really know a lot, at least enough about to consider and to look at them to potentially take action on them. And of those 6,000, about 2,500 of them are really the highly curated SNPs of clinical interest to like a functional medicine clinician. About 700 or so are pharmacologic, so how you relate to different drugs. Are you likely a responder, a non-responder? Are you likely to have a big impact from a drug or no impact at all or suffer side effects from it? And then about 3,000 of them are of importance in the data sets like the GWAS and ClinVar. In other words, certain characteristics seen in the genomic profile as it relates to different disease prevalence. So we're going to take a little look now in the system, and there's two ways to drive it, and we created it that way on purpose. There's the way to drive it stick shift, meaning like you're making many of the decisions and curating things as you go. And this gets easier as you use it, just like anything else. There's a bit of a learning curve, no matter how simple we can try to make it. And then I'm going to show you how you might be able to drive it in automatic mode, if you will. So the first app within the Opus system or platform we're going to look at is basically called SNP Navigator. SNP Navigator is like the Google of the client's genome. It's a highly flexible search engine across the client's complete SNP database, and you can filter it by risk, type, magnitude, effect, many, many different ways. So this is the first screen where I have a lot of static screenshots out of Opus that I was working with the data set that I'm going to show you just so I have a very organized flow, and then hopefully we'll have a little time, we'll jump online and we'll actually bring it live and show you it, and we can ask it questions and things like that. So here is a data set on a client, and you can see over on the left hand there's all these different navigations, and I'm just using these red little circles I put into where I'm going to be clicking through. So in SNP Navigator, if you can see here, I just have a bunch of genes. There's SNPs. So within each gene, there's various SNPs associated with that gene. Then you see a column that's specific, just a little jargon about it that may give you a little bit of an idea of what the gene has to do with. It gives the risk allele. It gives the type. Is it a risk or is it a benefit? All these are risks showing up so far, so they're orange and they have an R in them, but there's beneficial SNPs too, and they would show in green with a B. And then the client's actual data. You'll see just the first three here. The person on the first one is null. They don't have the risk alleles at all. And then the next one's heterozygous, the next one's homozygous, just so you can see how those look in the system. And then there's a magnitude rating, which is how these are listed, by their impact or their likely function or the level of evidence in the data, in the medical literature, and then some key words. And this is a scrolling page. You can scroll down and down and down and down through all these SNPs, okay? You're just seeing one page here. So in this kind of form, it's not really that useful, but watch. If I'm concerned with the patient based on their clinical history, let's say, and let's say they have hypervigilance, right? Let's say they have anxiety, they have panic, they have insomnia, or they have PTSD, or they have fibro, or they have IBS, or something like that, I may want to take a look at, what's going on with this person's catecholamine-related genomics. All I do is type in the search box catecholamines, and now the whole thing is sorted by just the genes related to catecholamine metabolism. Okay, so you'll see all the different CompTs coming up first, and MAOA, and then on down through the line. Now, you may want to look through here and say, okay, well, I'm not really that sure what CompT really is. I've heard about it, Click on it. If you click on it, up comes an entire tutorial on CompT, right? So you can see here, catechol methyltransferase catalyzes the transfer of methyl groups from S-adenosylmethionine to catecholamines, including the neurotransmitters dopamine, epinephrine, and norepinephrine. And the O-methylation results in one of the major degradative pathways of catecholamine transmitters. So this is how we cycle them out, right? And we're making more. We have to keep a balance of them. So if there's problems along these pathways, you can get neurotransmitter imbalances, and it can relate to clinical disorders related to that. So if this seems to resonate with the person in front of you and their clinical situation or their family history, whatever it may be, you may elect to curate it. Curating it means you click the curation button, it goes to the patient's client-side report. You're adding it to the report for the patient, okay, that you're going to talk about. So not everything you see will be generated to the patient, right? This is a very large data set. We need the clinician to kind of figure out what makes sense for this patient given their scenario. Now, the description here of CompT may be too heady, right? This is for the doctor. But if you want to see a simplified version, let's say for the patient, then it transforms it into simplified language. Basically keeps it easy. CompT gene helps break down the neurotransmitters dopamine and epinephrine. A defect due to certain variants in CompT will cause higher levels of dopamine due to slower breakdown, which can contribute to anxiety, insomnia, and individuals may have mood swings and so forth, right? You can curate this description to the client-side report so they can look through that. So then once you're in the gene CompT, you can see that there's a multitude of SNPs reported, and this system will go in a much more robust, complete analysis of different SNPs related to genes than you're going to see on a static, what we're used to, like a toxigenomics panel, right, or an estrogenomics panel. These are small little collections of SNPs or genes with limited number of SNPs that we're used to on these static things. We're dealing with a much bigger data set right now. So you can see this person is hetero on this CompT SNP right here. And if you don't know what that SNP is, you can just click that and this whole screen scrolls and tells you everything you'd ever want to know about that specific SNP, including what kind of agents would modulate it. But this is all cool, and you can parse this a million different ways, but where it really gets interesting is when you get into more high-level analysis like network mappings. Network mappings are networks and biochemical pathways embedded within the clinic, within the client's data. So it allows you to really contextualize everything across metabolic pathways. The color codes are there: orange for homozygous risk alleles, yellow for heterozygous, gray for null or not represented in the client's data. A directional arrow means that's the way metabolism is going. A transverse line is an inhibitory effect. A line with the circle means you're dealing with a molecule metabolized by the gene or produced by the gene. So when we get into network mappings, you'll see a list generated here, and this is just a partial list because, once again, the screen keeps scrolling down. But you can even just see on this first page, You can look into adipocytokine signaling, catecholamine metabolism, circadian rhythm, estrogen metabolism, 1-carbon or methylation metabolism, oxidative stress, gene expression, phase 1 detox, phase 2 detox, vitamin D mediated expression, and right on down the line. So, and then within each of those little things, you can see in a checkmark system the different areas where there's genes or SNPs in there in subcategories like inflammation, detoxification, methylation, metabolic SNPs, oncogenes, things like that. So let's pick one. I'm just picking the one that most people probably have the most familiarity with, like 1-carbon metabolism or methylation. In Opus, this is how it looks at it, okay? It's not just each SNP as a number and it's hetero or homo. It's looking at the whole metabolic map in methylation, and it's then overlaying the patient's genomic data on the metabolic map. So you can see in each one of these different genes here, it's filling in those same kind of colors of hetero, homo, or null. And it's almost like looking at the battery power indicator on your cell phone. So you can quickly look across a metabolic map and say, let's start with, where's all the orange stuff, right? Where's the homozygous representation across these genes? Now, I know in 1-carbon metabolism, everybody's seemingly obsessed with methyl tetrahydrofolate reductase, and that's circled in red. But it's not the only thing to consider, right? It's what everyone is focused on. But look at this metabolic map. How about that fully orange box up there, right? There it is, food 2, right? What is that? I mean, I know some of you probably don't. But if you don't, you can click on it. Let's see, what is this thing? This is fucosyltransferase 2, or FUT2. It's a gene inherited from both parents, and it determines your secretor status, or the ability to secrete your blood type antigens into the body fluids, sweat, saliva, digestive, mucus, etc. There are many health issues linked to non-secretor status, including susceptibility to a broad range of chronic diseases, imbalances in gut bacteria, or dysbiosis. So people with this aberration here are much more susceptible to dysbiotic states in the gut and less functional intestinal membrane integrity. So mucosal problems at the gut level, leaky gut, hyperpermeability. And this is getting into, this fructose, right? This is a sugar. So this is now diving into glycomics in a way. And we're seeing now the rise of systems glycobiology or glycomedicine. And in fact, when you look at, like, let's say dietary predilections of not immunologically tolerating different dietary kind of strategies based on blood type, you're dealing in glycobiology. So this is really popping heavy now. So a lot of people didn't even understand that concept of blood types relating to someone's diet and how it might impact them. So they just said, oh, that's ridiculous, right? No, it was writings by a guy who was 30 years ahead of the medical literature. That's what it was, right? So there's incredible science behind that. And we've known forever that people have much different predilection toward cancers and different subtypes of and cell types of cancer and different chronic diseases based on their blood type. And a lot of it has to do with glycobiology and their secretor status. So we can dive into some of these relationships. But even looking in pathway analysis is a little bit simplistic, and Opus really dives deeper than that. Pathway modeling doesn't take into account the complete flow of information, all right? Because it's really more of a network. And networks think, they learn, they respond, they react, they're computationally active. So if we're looking across some of these SNPs, or genes in methylation, and let's say we have problems in some of them, we want to know what do we give to try to patch that, right? What are the therapeutic agents we want to do? And you can see this is a mapping within Opus of some of those things, and we want to try to kill multiple birds with one stone. So if you look at some of these agents that we're used to using in 1-carbon metabolism, 5-methyl tetrahydrofolate, cobalamin, methionine, betaine, pyridoxine, and so forth, you can see many of them are mapped here. And it shows, for instance, that they're in green if they have a unitary action on one SNP, but it shows that or in one gene, and it shows that they're in blue if they have multiple actions on multiple genes. So we want to try to find the highest value type of interventions, and if we can kill two birds with one stone, the system can help us find these things. So let's look at just real quick phase 2. If we want to look at phase 2 detox, in this data set, I pop this up and I'm going, boom, I got a problem here on glutathione reductase, right? You can see it's all orange. So if I drill into that, it's telling me here, it's a central enzyme of cellular antioxidant defense, and this reduces oxidized glutathione disulfide to sulfhydryl form of glutathione, which is an important cellular antioxidant. And if I look down at the patient's data here, I got some problems, right? I got two major SNPs that are homozygous and one that's heterozygous. So this is something I may want to curate and add to the list of things I want to dive a little bit deeper on. And I can look into gene templates. So I can look at it a bunch of different ways. I can arrive at the conclusions in different types of ways. So templates are collections of SNPs that are organized around a central function, and you allow the system to sort of auto-curate the information for you. So if I am worried about a woman's estrogen state, right, and their risk for breast cancer and things like that, I can simply call up the complex template related to estrogen genomics, and you can see it shows me all of the genes around this radial diagram that are related into estrogen metabolism, and then the length of the different spikes coming out on the radial diagram are the number of SNPs related to those different genes, and embedded within those long columns, the longer the column, the more SNPs, you can see the patient's data that's sort of overlaid onto that with the nulls, the hetero, and the homozygous representations, and even the beneficial ones would be in green if there's any beneficial SNPs there. So I can quickly look down through a lot of different complex templates and figure out where the patient's genomic problems are in which different types of domains. And then finally, we'll look at multi-SNP macros, and then I'll start looping this together for you. Multi-SNP macros are really important if you're really trying to determine what is the highest level targets. You can't just go one SNP at a time and look at it myopically. And what Opus will do is use network algorithms and say, if X SNP is present in this state and Y SNP is present in this state, then we might have outcome Z. Right? And that's what these other static kind of reports are not very, very good at doing. It's a very important tool within Genomic Insight and Opus-23 Explorer. It allows for better clinical decision making, and it lets you just leave that one SNP, one disease correlation kind of reductionist thinking. An example of this is let's go back again to methyl tetrahydrofolate reductase. You can't just look at one SNP. You need to look at the combinations of the patterns in the SNPs to really know what the metabolic impact is. For instance, if you're like this patient's data here, they are null on this C677T, but they're hetero on the A129 8C. When you kind of network that together, this results in about an 8 to 10% enzyme reduction activity along that pathway, and even more for children. But you can stratify this across all the different permutations of the different SNPs on that pathway and get a relative indication of where the patient's functionality is likely to be. Then we're pivoting and we're turning then often to the metabolome or the proteome or organic acids or whatever it may be to look at the actual functional impact of what we're seeing genetically. Then on prescriptive tools, we can go in and we can run the patient's genome or their data set against drugs. Right? So this patient, let's say they're on a statin drug, they're having pain, muscle ache, fatigue, and they're just not doing very well. We can just pop their data set in, and in the search box in the pharmacogenomic database, I put in statin, and look what pours out. I find out that they're pretty decent from a genetic standpoint with toleration of statins and the intended effect of statins, but I would probably avoid rosuvastatin, or I would look at the dosage of rosuvastatin. It might be a good choice because they have a greater response to that drug therapy, but they're more likely to be overprescribed it because of that. So if they're on 40 milligrams of that statin, that may be why they're having the side effects, and they may be able to take 10 milligrams and get the effect that someone else may need 40. So you would never know that without mining this. And also in the natural product side, if I'm looking down through their genomic data, we can come up with natural agents that have the highest target value on as many of their SNPs that have dysfunction as possible. So we're coupling not only the genomic data, but also the reported medical literature in PubMed on these different types of relationships. So if you look here, this is just a patient's data set. I didn't pick any specific SNPs or genes or any specific functions, just let their whole data set out there, and I ran the natural agent query, and when it's run, you can see the different types of natural agents coming back, and curcumin leads the list in this patient. And you can see, we even have all the numerical data if you want it, the number of genotype hits that the system made in connections. So all the different SNPs that there may be an impact of curcumin in this patient, but functional hits, what kind of different functional pathways, gene hits, it's actually at the gene level, and then PubMed hits, okay? So you can really find high-value agents for these specific individuals. But I must tell you, if you run their whole data set and you run it patient to patient to patient, you'll see a lot of the same things leading the list. You'll see curcumin, you'll see resveratrol, you'll see vitamin D, you'll see omega-3 fatty acids, you'll see quercetin. Why do you think you might see it in so many people? Because Opus doesn't have favorite nutrients. It doesn't have their favorite herb. It just is what it is. It's a number. The nutrient, the herb, the nutraceutical, it's a number in the system, and it goes out and pings all the databases and tries to figure out where's the evidence on these for different things. So it's just reporting the hard, cold facts, okay? So why does curcumin often lead the list? Because it's had the most research on it of anything in nutraceutical land in the last decade, all right? It has the most volume of new literature, so it's rated higher. All right, so I don't run the natural agents on the patient's whole data set because I usually get similar information. I want to drill down to what I think is most impactful in that specific patient based on their whole medical history. And here's curcumin to Opus, okay? It's not this beautiful, rich, golden kind of, powder. It's just this. It's data, right? So we know what curcumin does, right? One of the things it does is it has a lot of impact in inflammatory situations, right? It's a great anti-inflammatory. Well, look at its genomic map. It's a strong, strong antagonist of NF-kappa B. This laser pointer isn't great, but you see that there? See the length of that right there to NF-kappa B? I don't know if I can, these screens are almost parallel with me, but also COX-2. Down here. So it's antagonizing NF-kappa B, cyclooxygenase 2, of course, it's a strong anti-inflammatory. But what about, look at this, it says it has a lot of impact on mTOR, MAOA, and so forth. So if I look down, scroll down a little bit here, look down into here, I can say, okay, well, what is this stuff about mTOR and curcumin? You see those little numbers there under the PubMed column? Opus does this all day long. Click on it. It gives you the citations that it attaches to. So it's giving you the abstracts, and then you can click on the PubMed ID and be right out to PubMed or to full text on the article. It's embedded all the way through. So one of the advantages, besides it being a clinical tool to use to try to determine what to do with your patients, is the mere fact that this is the best genomics class you will ever take in your life. Just keep working with patients and drilling down, and you keep clicking on stuff, and every time you click on something, you learn something, right? This is not stuff you can learn in a classroom, right? When I went to medical school and nutrition training and all that, none of this stuff was even around, right? So I didn't know hardly anything about this stuff. So you have to either just go back from scratch, which is almost daunting, or you just start using a system like this and you start learning about these things as you go. Because there are the higher impact ones that are impacting more and more of our patients versus other ones. So even on mTOR, you can query the system, and on mTOR here, you can see curcumin. It's a downstream bottleneck agent of mTOR of pretty high significance, but there's a lot more of them too. you can just keep reading through them right there and their relative effectiveness. And on the other side, you can see the upstream stimulating agents of mTOR in the natural realm. So you can go really get very, very precise with your prescriptives based on the patient's information. You can even do it a different way. You can go into Logos AI and use AI or network theory to try to find out what is the highest impact natural agent that you can use to affect the specific genes you're trying to affect in very specific ways. So this is truly precision medicine, utilizing requisite variety, which is part of how you do network analytics. So this is a screen here. You can curate and select and send different genes to this kind of screen here. And then through these radial buttons, you can pick various genes to downregulate or upregulate in a strong, moderate, or weak manner, right? And you can build different sort of matrices on what you're trying to accomplish and then run it, and it'll tell you what natural agents to use and the most efficient way to hit all those targets you're trying to hit. So here's one of our genes in one-carbon metabolism or methylation, one of the ones that's sort of the poor stepchild, right? It's not the methyl tetrahydrofolate reductase, that's the star, right? But this is a very, very important one right here. And hey, what is this? Well, this is a mouthful. 5-methyl tetrahydrofolate homocysteine methyltransferase reductase, right? That is why they call it MTRR, right? Who wants to say that every day? But this is the most common downregulated SNP and significantly found to fail to reduce B12 for methionine synthase reductase to make methionine. So this is a problem in one-carbon metabolism quite frequently in people. And here's our little diagram again, which I showed you on a previous slide. If I want to try, if the patient has problems like I do in both of these genes, you're wanting to find the natural agents that are going to make an impact on both of them. So in this case, 5-methyl tetrahydrofolate, a methyl donor like betaine, maybe methionine, B12, or some form of cobalamin, and pyridoxine or P5P, they would all be good choices. But check this out. In my role as a product formulator, at DFH, we use this kind of analytics all the time in how we're putting together novel formulas to do very specific things metabolically. So on this page here, I'm basically selecting, you see I put a couple of different genes in here just to run an example for you and did a screenshot. Can you see those laser pointers or not? I can't see them on there. Let me go back to it. Okay, so I put in here agonize mTOR, agonize, which means upregulate, right? NRF2 and SIRT1. So, you know, I'm probably trying to design a product formula for longevity, right? Anti-aging. Look what it spit out on the bottom. Resveratrol, nicotinamide riboside, omega-3 fatty acids, nicotinamide also, you wouldn't use them both, right? But it's hitting different PubMed and different evidence bases on nicotinamide riboside versus nicotinamide, Mediterranean diet, berberine. So if I wanted to try to start putting together some sort of formulary product to hit these different genes in the way I want to, I can query the system to tell me what to use, right? And it's all linked to different evidence in the database. So the next thing is Curation Navigator. This is just talking about how you pick different things within the system to send to a client-side report. And as you go through, whether you're looking at different genes, looking at different SNPs, looking at different metabolic pathways, whatever it may be, you can hit the curate button. That means it's sending it over to the client-side report. You can pull up the curation editor and you can see what genes or SNPs did I send over to look at with the patient or review with them. What complex templates, so things like estrogen genomics, thyroid genomics, phase 1 detox, whatever it may be. Which different multi-SNP macros, which network maps, so you can show those flow diagrams, and which prescriptive agents. Now this is a lot of different things in check marks. I would never pick this many to send to a client-side report. It's just too much information for them, and it's too long of a report. I just wanted to show you what it looks like. But let's take a brief look at driving this thing in automatic instead of stick shift, all right? So, because what I showed you before is a lot of the like in-depth functionality where you're driving in like Opus Pro. But the average clinician doesn't necessarily want to make all those different decisions and doesn't want to drill through it all. Some do, some don't. So what we created is a very simple push the button kind of auto curation thing called Report Wizard. And right now we have 12 domains. So they include methylation, detoxification, cognition genes, inflammatory genetics, anti-aging, endocrine, structural, so musculoskeletal kind of stuff, bone, energy metabolism and mitochondrial, estrogen genomics, androgen genomics, cardiometabolic genomics, and gastrointestinal genomics, right? So it just divides it up into all these different clinical domains for you. So you can just go boom, hit the button, and basically Opus curates all the impactful genes and SNPs and natural agents and all the different things that you might want. And we limit it right now to 3 different domains on any one client-side report. You can go back and run a different 3, but 3 at a time on a report because otherwise the report gets too big, right? Remember, this is a big data set. Genes don't change. You only have to run the gene data set once. There's no retesting. It doesn't change. What changes? What we know about them. Right? The medical literature emerges, the data sets change, different connections are made. Once you have the data set, it lives forever. You can keep coming back and mining it in the system. Let's say the patient develops some other symptoms or something pops in their family history that wasn't there before. You can go back and run the reports on that stuff or the genetics. You just take one bite out of the apple at a time, okay? But think of this. How many times have you run a detoxigenomics panel? Or an estrogenomics panel, or a methylation, 1-carbon metabolism. You don't got to run individual panels anymore. You got it all, right? Boom, hit the button. Next month, hit a different button, right? That's where it's going. The data is just too easy to get. You get it, you got it. And then it's all about managing the data. It's not about acquiring the data anymore. So let's look, and after you select your buttons up to 3, then you can just easily on this drop-down menu decide what do you want to send to the patient you're going to review with them or spit out of your printer and you hand them or you send it to them as a PDF. You can include the network maps, all those metabolic pathways in whatever area you're picking on your big radial button there or not. You may say, this patient's a real kind of wonky patient. They love all the technical stuff. They want to see all the detail. Send them the metabolic maps. Someone they don't care, just tell me what to take, doc, right? I'm not sending them the metabolic maps. Their head will explode, right? But I got engineer patients who want the metabolic maps, and then they're asking me for more, right? So it gives you the flexibility. Include introductory explanatory text. It tells them what's a gene, what's a SNP, right? What's epistatic? What's epigenetic, right? It gives them just a basic explanation up front. You can include that or not. Include non-risk SNP genotypes. So if you check that box, it'll also report on their client-side report which genes were negative, like which SNPs were null. So you can just have it spit out the things that have a problem, or you can have it spit out things that have a problem and the things that were null, because some patients want to know. Well, I don't see the 67TT, I don't see that. Where's that? Well, it's not on there because you didn't have any problem there. Well, I want to see that. You can put it there, okay? It's really up to you. Just makes the report a little longer. Include high-value agents. These are the different things like the nutrients, the nutraceuticals, the dietary, the different exercise prescriptions, whatever it may be. What are you going to do to tell the patient to do or take to impact the cards that they're playing? Include possible drug interactions. This is where you're listing out on the client-side report the drugs that they need to be careful with or the medications based on their genomic data. And then we have in here as an optional, it's totally an optional thing. You can suppress it or you can turn it on, where the system also knows several hundred different DFH products and every constituent and every ingredient in it and how it hits all these molecular targets as well. So if you use that line, it's very nice. If not, you can just do the generic and apply it to whatever prescriptives you're using. So I'm going to give you an example of running the report wizard on a data set and just picking that simple button in wizard of methylation and detoxification. So I only picked 2 domains, okay? So And I did that drop-down box, and I pretty much put yes to everything. So what you're going to see in the end here is the client-side report. So here I have a little bit, it tells the patient a little bit, now this is in patient language. What is Opus Explorer? What is this system that's generating this for them? What are the two different domains the report is focused on, in this case, methylation and detoxification? And then sort of welcome to your owner's manual. This is where it tells them a little bit about what's a gene, what's a SNP, what are all these basic terminologies that they're going to be able to see coming out them. And then a little bit of a tutorial for them on what the colors mean. So it says here, you can see these relative power and color bars. The orange is the sum of the significant SNPs in genes that indicate a higher or homozygous risk are in orange. The ones that have a more minimal or lower risk that are heterozygous are shown in yellow. The ones that are null are gray. And the ones that are beneficial, that impart a benefit, are in green. So they can understand that as they go through the report. And then in the first section, detoxification. It shows the radial diagram of detoxification genomics, all the genes around the outside, and then all the different sort of radials are the number of SNPs in these different categories, and it has the colors plotted on what their data is like. Sorry, hit the wrong button there. Okay, so then as I go forward, it'll go into each of the genes of consequence in them. So it tells them a little bit about the gene, gives them the power bars up top, and then actually lists all of the different relative SNPs on the bottom and their specific results, and a little bit of text or keywords about it. And these are the discussion points. You can sit down with the patient and talk to them about, hey, CompT, this is basically what it does. This is why I'm concerned about this with you in your clinical scenario, with your anxiety, with whatever, and this is why we may be doing something to give you prescriptively to modify the function along this pathway. Here's glutathione reductase. They were homozygous here in one of the SNPs. So this may be something where we're giving them glutathione, or we're promoting phase 2 detoxification more globally, or we're trying to do something to limit their toxic exposure, whatever it may be. And I chose to put the metabolic map for detoxification on here. So it shows them. So I find them useful. I can say, listen, you don't need to understand all this, but look, see where I'm narrowing in on your genomics of detoxification? Look at that box up there on the top that's all orange. That's telling me that's where there are problems. And that's that gene we just looked at. Homocysteine, I can pivot to that. And we can talk about what homocysteine is, what one carbon metabolism is, how homocysteine is a risk, how methylation defects can affect their health, and it's the same thing. And this person here's methyl tetrahydrofolate reductase, and their actual data being displayed, and I just drew arrows to instead of just the RS numbers. A lot of people are more familiar with the C677T for the RS1801133 and the A1298C for the 1131 RS number. So you can see in this person here, they're homozygous at this C677T, they're hetero at the A1298C, and in the other main one carbon or methylation SNP here, the MTRR, they have some dirtiness as well. So when you matrix this all together, where do they plot in the multi-SNP macro? Significant downregulation, 60 to 70% reduced enzyme activity, right? This is someone saying, listen, this is an impact. We need to do something here. This is why I'm giving you 5-methyl tetrahydrofolate, or this is why I'm giving you, homocysteine supreme, or, fill in your product that you use, whichever one. Then they have an understanding of that, and then the metabolic map for homocysteine genomics. And then you can send out just the generic natural agents to the report if you want. And if you look at this, you see the relative power bars in blue. This is the strength of the recommendation out of the Opus database in this patient's 2 domains that we picked. And you can see here in homocysteine pathways, look what's leading the list: folic acid, right? And then riboflavin, betaine as a methyl donor, omega-3, resveratrol, omega-6, pyridoxine, cobalamin, right? 5-methyl tetrahydrofolate. Now you might say, well, why is it ranking 5-methyl tetrahydrofolate number 9 and just B9 folic acid number 1? I know that I should give them 5-methyl tetrahydrofolate, right? Not folic acid, not synthetic folate that's in, food supplements and cheap cheap nutritional supplements. Why is it ranking folic acid higher than 5-methyl tetrahydrofolate? Anybody want to know? There's about 100 times more research through the decades on folic acid and homocysteine than there is 5-methyl tetrahydrofolate, right? So this is where you need a clinician's mind too to go, oh yeah, I get why, but I'm going to give them 5-methyl tetrahydrofolate because that's a better form, right? Opus is not going to make that kind of decision. It's going by the data. It's a data-driven animal, right? We need to put the sort of the human touch on top of it. And then you can report to them their drug genomics. And the tips for curation, if you are driving at stick shift and you're making these selections and these decisions as a doctor or a clinician or a nutritionist, a couple of things to remember. Clients don't really understand SNPs. They understand genes. So when I talk to them, I try to keep it at the gene level, not the SNP level. Okay? The SNPs get into the weeds too much, even more than the genes. Number 2, don't overwhelm them. More is not better. Take it in chunks. I would even recommend even doing one domain at a time. Just deal with their cardiometabolic genes, or just deal with their detox genes, or whatever you want to do. Don't do it all at one time. Curate clinically relevant data. If it's not going to influence what you're going to do in your care, unless it's something really screaming that you really need to address with them, just leave it out. Don't even include it. And like I said before, the data is for life. Don't try to cram it all into one visit. And allow the client to read the report, digest it, and revisit it at future appointments, right? You can review it with them initially, but then send them off with a little homework assignment. Just take a look over this, digest it over a little bit of time, and then any questions, let me know. But in the end, probably 95% of our clinician users are using Report Wizard. They're not driving stick shift. They're driving automatic, right? They're picking different domains and letting the system do a lot of the work for them, and they just take that sort of in chunks. Now we're also adding on, there's an add-on module that we're working with to kind of loop all this together called Utopia that does very similar things through the microbiome. So it's using all the metadata sets and all what we know about microbiome and allows us to parse microbiome data in a bunch of different ways too. Instead of just a static report giving you information, oftentimes about a lot of organisms that you really don't know anything about, you don't remember from microbiology, and they didn't even talk about them in class anyway, right? So what are all these things? But you can query the system here, and you can go mine it for, how about my probiotic elements? How about my food fermentation elements? How about my propionate producing or butyrate producing organisms? How about methane producers? How about histamine producers? How about, keystone species? How's my Akkermansia? How's my Fusobacterium prusnitzii or whatever it may be? Here's running butyrate producers, for instance, through the system. And then you can even go beyond that, and you can use different apps in the system just by radial button selection down a long list of organisms and say, hey, I want to increase Akkermansia, I want to decrease Clostridia, I want to increase Lactobacillus, and I want to decrease Fusobacterium, right? Tell me what to do. The system does all the network analysis on this, and it'll tell you what kind of dietary substrates, what kind of resistive starches, what kind of nutraceuticals, what do you need to do to move all those different things in all those different directions, which is really valuable because how many organisms are we dealing with on these microbiome things? Tons, right? How many organisms do we have in probiotics? You can't just give all the organisms you want to increase. You have to feed them to increase them. So you have to find the different substrates and combinations of substrates, soluble, starches and fibers and different botanicals. They'll move the dial on different organisms that you would never know if you didn't mine it through a system like this. And many times you're kind of once removed where we may not have any agent that will selectively down-regulate one specific organism, but the system can find out what organism can we upregulate with a substrate that downregulates the organism we're trying to, like we can go boom, 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 boom to get where we want to go, right? That's cool stuff, right? We'd never be able to figure that out on our own as clinicians. So basically what we're trying to do at DSL is ultimately the goal is to build an entire spaceship for the clinician, right? A portal in front of them on their computer that they don't have to leave and go to this system and that system and everything else that will loop together all this data analytics for them in a clinical context to make decisions. So that means taking genomic information like we talked about today, in this case in the form of Opus, but microbiome information, metabolome and small molecule information, and have these systems that have the machine learning and the AI and all the different analytics behind them to be able to contextualize it all with your help and figure out what is the high impact things that you can do to really move the dial on their health in each of these individual omics lands, but then also crosstalk between them and do another higher level of analysis to find out what is really, step 1, step 2, step 3, in a triage type of way, how do you move the dial? And it's really going to become, I think, easier and easier with these tools. A lot of this stuff isn't even a invasive type of collection. SNPs is just buccal swab, right? Microbiome is poop, right? People don't love collecting it, but it's not invasive, right? We can do a lot of metabolomics, small molecule stuff like that in urine. For some of it, you have to go to serum. So when you have to put the needle in the arm and draw and spin, then you're getting a higher barrier of entry to many clinicians. But the ultimate thing is to loop it together. And this is really going to be the future. So welcome to it. And we want to make sure you stay in the future lane, not the past lane, because this stuff is going to move very, very quickly. So if you don't mind, you want to indulge me for a minute, I'm going to go out into Opus. And instead of static screenshots, I'm going to just show you one or two little things that may be neat. I'm sorry?
How do you upload all the patient information?
If you run Genomic Insights, it's delivered to you as a file in your portal as a clinician. It's not, no, Genomic Insights, the test by DSL. That allows you the access to Opus-23 Explorer. The data set is delivered to you through it. The other way to get, you'd have to go to Opus Explorer Pro. You'd have to go through the training on Opus Explorer Pro and be an authorized user. Then you can bring different types of data to it, 23andMe or Ancestry or what have you. So that's an option. But you don't have the report wizard kind of functionality in there in the same way. You could use Opus Pro with report wizard functionality, but you'd have to get the Genomic Insight data set. You can order it two different ways. You can order it where it just comes through into Explorer, Opus-23 Explorer, or you can get the data set, which is a different ordering thing on the rec form, and then you get the data set delivered. You can put it into Opus Pro, or you can bring it to any other genetic genie, like more simplistic genetic genie, if that's what you prefer to use. Right now, I'm going to load up my data set right here. So when it comes up, the default screen is just these different report wizard domains, right? But let's say I just wanted to go into SNP Navigator on this patient. I'll pretend it's not me. It's just what's going on with this patient. So this is just, and they have it at a resolution that makes the screen bigger here, so I can't see as much on a screen as I normally would. But I can see, this just scrolls down with, page after page of the person's SNP. So it's not really that useful in this form. It's listing them by magnitude for me right now. Let's say I wanted to know, well, what's really impactful on this patient? What is homozygous? Well, in the search box here, how about I just put ++, right? Oh, that's homozygous in the system. Now it's giving me my highest magnitude risk homozygous and my beneficial homozygous report here. So here I can see really quick, this person has at least genetically a higher likelihood for Parkinson's disease because of this gene. I may have some trouble with the BCO1 converting beta carotene to vitamin A. I may have some problems on IL-13 in that I may be more likely to have more inflammatory kind of conditions, because if I'm not producing IL-13, I'm not downregulating some of the granulocyte activity, HLA-DQ82, MTHFR. So let's drill into MTHFR. So here we are again. It's telling me about MTHFR, if we didn't know already. but it's drilling deep into the sub-SNPs of MTHFR, and it's giving me some conclusions here. Do I have the kind of pattern analysis that would mean I have an MTHFR polymorphism pattern that would affect my homocysteine levels directly? The system is telling me unlikely, false, right? But I do have the kind of polymorphisms that it would affect enzyme activity to some degree. I would not have an increased toxicity to methotrexate. But if I go down and just look at the SNP data here, you can see on C677T, I'm homozygous, and the other one you're used to seeing is A1298C. Right here, I'm heterozygous. So if I keep coming down, these are all literature citations you can pop out to if you want. But look at the agent fingerprint expression here for methyl tetrahydrofolate. It's showing me the different relative strength of the different agents I might want to use. You can see here folinic acid, betaine, riboflavin, methionine, cobalamin, right? So all the things that we know to use. And all of this is clickable. You can, if you click on that, it'll tell me about folinic acid, right? If you really want to know what that is, you weren't sure. See, it kicked me out real quick. So if I come back here and I say, okay, well, you know what? I'm not sure I know too much. What is this 5-formal tetrahydrofolate, right? I can go learn about that, and it gives me the genomic fingerprint on how that is affecting, and I can go out to PubMed, and I can read some of the biggest papers that the system is looking at to make these conclusions. It's really cool. I mean, do you have a system in your office that can do this, by the way? Anybody? This is incredible, right? I mean, I remember when I was in school blowing the dust off journal articles after going through the Dewey Decimal Catalog and putting quarters in the Xerox machine to copy one paper, right? This is unbelievable. I'm nerding out on it. It's just unbelievable, right? So let's say on this patient, I want to look at it a different way. I can go into network mappings, right? And if this patient's, let's say in the blood work, their homocysteine came back high, and I'm like, well, what's going on here? Well, let's dive in. Let's look at their 1-carbon metabolism this way, and we can look at the network map like I showed you before. Or my favorite way is actually go into syndrome templates. I can just scroll through these, and I'm looking for big orange splots, right? So in here, I might drill into these a little bit. Or, just to keep it on theme here, I can come down and in homocysteine, I got some high power stuff with orange. I can go in there and I can back around it the other way and drill in that way. Okay, so there's a lot of different ways we can go, but let me just run a report wizard to show you what that's like. So what do you want me to run the report wizard on in this case? Detox. Okay, let's run it on detox. And I'm going to include network maps, include introductory explanatory text, include non-risk SNPs, include low magnitude SNPs, so the ones I'm negative for, and the ones I'm negative for and the low magnitude ones, not just the big high value ones. I'm going to include the natural products as a table. We will not include the designs for health products, and we will include possible drug interactions, okay? You could. It's up to you. It's truncating the report to make it smaller and easier, so it's up to your style. It's just we try to give all the flexibility in here. So here's actually the client-side report. It's available to print out, to put as a PDF, to stick in your EMR, to do whatever you really want to do with, or to email it to a patient, send it through a portal, whatever you would like to do. So this is focused on detoxigenomics. It's giving you this little introductory text like we talked about. It's telling the patient what the different colors mean, what's homozygous and heterozygous, and then it actually gets into the data itself. So it's globally talking about detoxification with them, showing the gene radial diagram, and then it gets into reporting each of the different genes as you scroll down. Okay? So there's quite a few genes in detox, so it's a little bit long. You can reduce that by not including the high value ones. And then here's detoxification. Again, I must have left the tab on homocysteine and detox. That's what I did. So, but if we're running down further, we're going to get to the natural, here's the metabolic maps, cytokine. It ran a couple of different domains. I don't know what I did there. Okay, let's run this. What's interesting here is I noticed something, let's see. There's detoxification again. And then it'll go once through those to homocysteine, which is really methylation, one carbon metabolism. This is an older data set when we were still in beta, so it may be not throwing. These are the multi-SNP macros. I don't leave all these checkbox on most of my report. I was just trying to show you all the functionality here. So here's when you get into the natural agents and the power indicators. You know, quercetin, resveratrol, sulforaphane, rhodiola. A lot of this is hitting because of the detox section and their drug interactions right here. But let me show you something else as we're working to develop, like I said, this sort of dashboard for the clinician to deal with all of the challenges you have in your practice. And one of the things is, as these tools develop, I don't know about for you, but it's hard to go from like this system back to my EMR, back into my schedule. All right, you're like, where do I go, all this stuff? So we're trying to like put something together where it's kind of doing everything. And let me show you some of the kind of analytics we're going to be building into this full dashboard for you. Let me give you an example. Let's say you have a patient in front of you and they give you a bunch of symptoms, okay? This is a differential diagnostic algorithm generator, right? So let's say this is just a bunch of different symptoms that are all, you know, established in the medical literature and have codes in the medical literature associated with them. So let's just say this patient has fatigue, right? Let's say fatigue. Let's pick constipation. So fatigue, constipation. Let's find something else good. Hypothermia. So what if I said to you, someone's fatigued all the time, they're cold all the time, they have constipation. What's one of the things that might pop in your mind? Well, let's see. Algorithmically came out on top, see? But it gives you your whole differential list. But that's just an easy one, right? 3 common symptoms. But you get into a whole bunch of different stuff, the system can help you. It's like Dr. Watson. So we're building that kind of stuff into the system. And let's say they come in with some lab that you're not really, they come in with a bunch of lab work, right? And you say, oh, well, their WBC count, white blood cell count is very high. Their C-reactive protein is high. Their absolute neutrophil percentage is high, and their lymphocyte percentage is low. It's giving me probability tables of what diagnostics to consider, right? Which is pretty cool, right? And you can drill into it as deep as you want on how the data is reported. Or let's say functional labs. You can look up different phytotherapies and different botanicals and so forth. Well, this is the microbiota kind of function I showed you before. If you want to increase this bug, increase that bug, decrease this bug, and decrease this bug, it'll run you a map on different ways you can get there with different dietary substrates, herbals, things like that. So these are all, there's knowledge databases too, all built in. If you want to, let's say a metabolome database. Someone comes in and they have an organic acid test and you say, okay, I'm just picking one out of my head, methylmalone. It's not coming up that way. Methylmalonic acid, there it is, okay. It'll tell me everything about methylmalonic acid and then give you where you can get these diagnostics and all those kind of things. So it's just a really, really nice, we're trying to build as many of these features in. The other day, Peter and I were playing with coronavirus. So we were running data sets on what kind of drugs and what natural agents have any of the characteristics that we know in the mechanisms of action and acting on the genome that would be potentially effective against coronavirus, right? So you just run these through and you're seeing all these different nucleoside analogs, protease inhibitors, all the drugs with Vir at the end, right? Reverse transcriptase inhibitors, neuraminidase inhibitors. So these are the drug agents, but also look at all these traditional Chinese medicines that are neuraminidase inhibitors. They're already in clinical trials on these in coronavirus in China, by the way, on these different natural botanical agents in traditional Chinese medicine. And then further down, we'll get into the nutraceutical type of things. There's larch arabinogalactan, garlic is a neuraminidase inhibitor as well. So this is really cool stuff to have at your fingertips on your desktop. So that's just a little preview of some things that are going to be coming down the line as we build this whole sort of search engine for you guys to be able to play with and use on your desk and manipulate the data that's delivered to you. So once again, wasn't trying to teach you genomics, wasn't trying to teach you how to use the system. I will actually be doing a book signing at the DSL booth. They're giving away my FibroFix book. I'm signing it. If you want any more information on Genomic Insight, Opus-23, how to access it, you can ask those guys. They have a lot of training, a lot of webinars. And if you want to go even Opus Pro in a totally different way, Peter D'Adamo's group can facilitate that as well. So thank you. Hopefully it was useful to you. And I'll stay around here for about 5 minutes with some quick questions. And then I got to head over.